Hi Math 111. In this video we're going to continue our discussion of section 2.1 and we're going to talk about a special kind of a relation. Remember that we have a special kind of a relation and we called it a function, right? And we haven't defined what it is or given any examples of it yet. We've just seen this word function, right? And so let's actually do a definition, then we'll work with it. Okay, so here we are in our little definition page over here, right? And it says a function from one set x into another set y. Remember, those sets are collections of numbers for us. Okay, a function is a relation that associates each element of x with exactly one element of y. And that word exactly is really important, right? So let's consider an example for a second. So let's use a mapping to show a relation. So remember, we can use a mapping to show a relation by using these two circles, right? And these two circles, when we put some numbers inside of them, right? 4, 5, 6, just for fun, right? Remember, a mapping shows a relation by showing that values of the values here in this set here correspond to values in the other set here. And remember, we called these the inputs, and we called these the outputs. Right? And we said that one value over here in the input corresponds to a value in the outputs here, right? So 2 corresponds to 5, or 2 relates to 5, and we'll say 3 relates to 6. Okay, good. So this is a relation. It's shown by a map, right? Remember, there's lots of ways to show relations. We talked about those last time. Okay, but what we'd like to do is talk about a special kind of a relation called this function, right? Okay, and the restriction here is that it says that each element of x, where we have, let's say this is the set x over here, right? Each element in this set x relates to exactly one element or another thing in y, right? In a set y. Okay, so if we look at this example here, it is in fact true that each element in here, each number in here, relates to exactly one number over here, right? 1 goes to 4 only, 2 goes to 5 only, 3 to 6 only. Okay, so this one is an example of a function, so this is a function. Again, a function is just a special kind of a relation, okay? But let's look at another example. Okay, so let's consider another set of bubbles here, right? So we'll call this set x again, okay? And we'll call this set y, okay? And let's pick some different numbers. How about 3, 4, 2, and 1, 5, 7. Okay, so I'm going to draw a relation. I'm going to just pick one. I'm going to draw this one. Okay, so this is a relation. Remember, it's just a correspondence between the things that are in x, right, these numbers over here, and the things that are in y, these numbers over here, right? So this is a relation, but let's see if it's a function. Remember, a function says that each element of x, each input here can only go to one output, right? So again, what's important here is that each input goes to only one output. Okay, and that's the important thing that we're looking for here, right, in order for us to have a function. So let's see. Does 3 go to only one output? 3 goes to 1 and 5. Okay, that and 5 part is trouble, right? Because 3 can't go to two things if we want this relation to be a function, right? So that's trouble. What about the other numbers? 4 goes to 7. Okay, it only goes to one thing. And 2 goes to 7. Okay, that's also okay. It may seem like it's not okay, but remember that we're just concerned with each input going to only one number, right? It's okay if two different inputs go to the same number, right? That's okay. We're worried about a single number going to two different things, right? So really, this 3 right here is trouble because it's going to both 1 and going to 5, right? That sort of two arrow issue there, that's really what the problem is here. And so what that means is that this is not a function. This is bad, right? Okay, so not a function, and this is a function. Okay, so we have an easy way to see if maps are showing us whether we have a function, right? And another couple things here, just to work out some notation, right, is that these inputs here that we're making use of for this first bubble here, instead of calling those just inputs or set x or something like that, sometimes we get a little fancy and we use the word domain, right? So here we could call these values here in this first set the set of values of x here, right? The inputs, sometimes those are called domain. And the outputs here, this collection of numbers over here, the set y, sometimes we call that the range. And we're going to use those words a lot more throughout this term, okay? But really the domain is just the starting or x values here, right? The inputs. And the range is the outputs or the collection of the y's, right? Great. Okay, so that's one way that we can be able to tell whether a relation is a function or not, right? Maybe there's another way if we look at a different way to represent a relation. So remember, another way that we can represent a relation is by using a table, right? So let's consider for a second if we have a relation given to us by a table, right? Let's just say, what did we have? I don't know, let's just make it up. So how about 2, 4, 6, and 9, 3, 4, and let's just add one more value, 0 and 2. Okay, great. So this is a relation. It says x is 2 goes to 9, 4 goes to 3, 6 goes to 4, and 0 goes to 2. So this is a relation, but is it a function? So all we need to be concerned about, remember, is that each input here, and remember the inputs are going to be the ones here, the values of x here. These are the inputs. And these are the outputs. We're just concerned about whether each input produces only one output, right? Gives only one output number. Okay, so is there any value of x here, any number for x that produces two different y values here? Produces two different values for y. Well, no, 2 goes to 9, 4 goes to 3, 6 goes to 4, and 0 goes to 2. They only appear once each, right? So this is a function. This is okay. Okay, but let's maybe observe a relation in table form which is not, right? Okay, and these ones are pretty easy to pick out. So let's say 2 goes to 9. Let's say 2 goes to 9, 4 goes to 0, 4 goes to 3, 6 goes to, I don't know, how about 18? Doesn't even matter, right? Let's see. Does this relation here represent a function? Again, what are we looking for? We're looking for, is there an input which gives more than one output? Well, 2 goes to 9, 4 goes to 0, and 4 goes to 3. Aha, that's the problem. Right there. You see this right here? This stuff, all that, that's a problem because notice it's saying that 4 goes to two completely different numbers, right? Okay, so this is not a function. Okay, so not a function. That's bad, right? So this is not a function over here. And that's how we can tell just from a table. So what do we have to do when we have a table and we want to know if that relation represents a function? We just have to look in the inputs at the x values and look for duplicates, right? Notice that there was a duplicate here, right? Because there's two values of 4 and they give two different numbers, that's bad. That means it's not a function. Okay, and the same thing would work if we were to look at a set of ordered pairs, right? If we were to rewrite this relation here on the right as a set of ordered pairs, we would notice that we get duplicates again, right? Remember, sets of ordered pairs are written as a set, and we write the list of ordered pairs here. Right? And if we look at this relation here, we notice that there are duplicates again in the x coordinate of the ordered pairs right here, right? There's a 4 there, 4 goes to 0, and it says, oh, and 4 goes to 3, and that's bad, right? Okay, so because of that duplicate, that repeated x entry here, we know that this is not a function, and we already know it's not because of what we decided up here at the table, but now we can see that, again, seeing duplicates in the x coordinate there, in the x part of those ordered pairs would tell us that it's not a function. Okay, great. So let's see, what else? Let's consider an example maybe. Let's try an example just to see exactly how this is working. So I will choose one. I'll choose black. So let's determine if a relation does in fact represent a function, right? And I'm going to give you an example. Okay, so let's see. I'm going to give you a list of ordered pairs, a set of ordered pairs here. Okay, and let's determine if this relation is a function, right? Okay, so let's look and see if we can find out. I'll get a color here just in case we need one. So what is our restriction for determining if it's a function? What do? We look to see if there's a value of x that corresponds to two different values of y, right? Is there a value of x corresponding to two different values of y? Well, let's see. Let's look through our list of ordered pairs here. So let's see. In this one, it says -2 goes to 5. Okay. -1 goes to 3. Well, that value of x is not a repeat, right? Okay. 3 goes to 7. Well, has that value of x been repeated yet? Nope. And 4 goes to 7. Well, okay, no repeats in the x's. That's good. Is the 7 a problem? Is it a problem that both 3 and 4 go to 7? No, remember that's not a problem because we're just concerned about there being duplicates in the x coordinate, right? Okay, remember it's okay if you think about your mapping for a second. If you like drawing the mapping, we could do this as a mapping. If we said -2 goes to 5, -1 goes to 3, 3 goes to 7, and 4 goes to 7. Okay, this is what the mapping would look like for this relation, right? And is it in fact a function? It is a function because there are no inputs over here that go to two different outputs, right? So yes, this is a function. It is a function. Function. Okay, great. Perfect. Okay. So sometimes we like to use some special notation to denote a function, right? You may have seen this notation before. Let's just see. So usually we use this notation when we're working with equations that represent functions, right? So let's see what this notation would look like, okay? So let's maybe call this notation. Okay, so let's see. We use notation that looks like this. Like F for function, right? That would be a good letter to use. And then we have this like parenthesis X stuff, right? Okay, and this says F is a function. And what are the parentheses for? These are not multiplying parentheses. These are not like, it does not say F times X. Okay, so maybe make yourself a note that says this is not F times X. Okay. That's not f times x, right? These are function parentheses, right? This says f of x. That's how we read that. Okay, so we read this as f of x. Okay, and we specifically reserve this notation for functions, right? Okay, and what does this notation actually mean? What this means is it tells you the value y that x corresponds to under the function rule or the function relation called f, right? So if we had our mapping back here a second ago, right, where this was a function, I could have labeled this as a function that goes between this set here, this domain, right? Remember, this could have been called a domain, okay? And this could have been called a range, okay? I could have labeled these two things and I could have said that f is the relation or function relating this domain to this range, right? Okay, so I could have labeled this function as f, okay? And so when I write something like f of x, then what I'm really doing is saying, well, this is going to be the value that x corresponds to. So, for example, the y value that x corresponds to. So, for example, back here, I could have said something like f of -2 equals, and I could say, so the value of the function, right? So what does -2 correspond to under the function f? -2 corresponds to 5, and that's written just like this, right? So when I write this kind of a statement here, this is saying the value of -2, the value -2 corresponds to 5 under the function f, right? Okay, I don't want to have to write out all of those words, so we write this nice compact mathematical notation here, right, to say what the value -2 corresponds to underneath the function f, or under the relation f, right? But it's specifically a function, so let's be specific, okay? Another one would be, for example, I could write f of 4. What is f of 4? Well, it's going to be what? What is the corresponding value for 4? Well, the corresponding value for 4 is 7. So f of 4 is 7. Okay. Now you can't use this notation for just any relation. Remember, it's got to be a function, right? You have to be using a function here to make use of this notation. Okay, so make sure that if you're trying to use this notation, you're using it with a function. Okay, you can't just use it with any relation you want. Okay, so we have another way, sort of, another word to use when we're making use of this notation, right? You can also say that if you have a value in the domain, right, in the set X here, if you have a value in the domain, then its corresponding value in Y, right, under the function is called the value of the function, right? So I could have gone back here and I could have said the value of the function when x is -2, right? When my input is -2 is 5, right? And so this would be the value of the function. So 5 is the value of the function. 7 is the value of the function when the input is 4. 5 is the value of the function when the input is -2. Okay, and those are again words we can make use of. Okay, for right now, that'll be good. We'll continue with another video on section 2.1 for next time.